In this video, we'll start our discussion of section 14.8. It's called the Jacobian. Let's begin by discussing what the Jacobian is. Mainly the big picture. We're not going to go into technicalities of where it comes from or anything like that. Recall back in Calc 1 that you would do just a normal integral problem, and we'd have some issues maybe with our function inside. It just wasn't playing nicely, or maybe a function inside of a function, and we would do what we call the U-sub. What we're actually doing with this U-sub is we're changing this axis from A to B, and we're reforming it using some kind of rule like U equals x plus 2, and it changes my A to B to some new axis, and maybe it stretches A to B across 1,000, right? Maybe now it's at 1 over 1,000. All we're doing is recreating these U's that make it something nice that we want to talk about. We do this in conversions all the time to make things nicer for ourselves to think about. You guys are going to do this in DiffEq. Substitutions typically are the key to all mathematics for a lot of it. So back in Calc 1, what you did is you changed the AB axis on the x-axis to some new values C and D on what we called a U-axis. Now, we never drew this U-axis. We just thought about it now in terms of U instead of X, which means that we created a new axis. We are going to do that here over some shapes that we have been integrating with double integrals. And you may not have this in this text. You may not feel like they have been simple, but like most of everything that we have integrated over was either some kind of rectangle or square and some kind of shape like that, or some kind of circle or ellipse or some kind of circular region. Now, the problem is, what if it's not rectangular? What if it's like a diamond or a very small region like this that is a parallelogram, or what if it is a giant oval, right? An ellipse that's not pretty or turned to the side. What we're going to work on here is this is a U-sub idea, but for double integrals or triple integrals. So this is called the Jacobian. He was a mathematician. We're not going to get into the technicalities of it, but what this says is we're going to have new equations to turn x and y into u and v or some other variables. And what we're going to do is we're going to change the integral. One, what this means, and we need to get used to this because this shows up a lot. Hopefully at this point you're already thinking about this. When we see this, what this means is it just took the function of f here, and it was in x and y's, and now it's in u's and v's. That's all it says, is that this is going to be like x equals u plus v. This is going to be like y equals u minus v, something like that. And we would take that, and what that blue there means is just go back to this function, and everywhere there's an x, I want you to put u plus v, and everywhere there's a y, put u minus v. All right, this makes sense here, du dv, right? Changing it to that. And then we have this thing that just sticks out here, and I'm going to highlight this. You will forget this at some point. I forget this at one point. You've already dealt with something like this, and I'll show you in here of where that comes from, but of something that I'm mentioning, it doesn't make sense until we get there, but we have to introduce what is called the Jacobian. Now, they have some crazy definition for this using that partial sign. Ignore it. That's just the ratio between the change in x and y versus the change in u and v. We're not going to ever use that. We're going to use this. What this is, and it looks maybe way complicated to you, but those are just partial derivatives. Given an x, take the partial of u, given n v, and u and v, and then remember the straight bars take the determinant. I think it's spelled that way. Determinant. And how we did that is we would multiply, subtract, multiply. So let's give this a shot. Let's find the Jacobian here. This is going to be the thing that we're going to have to introduce to our quote-unquote three-dimensional U-subs. So we need to find each one of those. So j is equal to, right? It's the partial of x with respect to u. Right? Let's write this out. Partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. You can see it's pretty easy to memorize. Just goes through each one. All right, so the partial of x with respect to u is 2. The partial of x with respect to v is 1. Y with u is 2u. Y with v is minus 1. And then we find our Jacobian. Right, so it's 2 times negative 1 minus 1 times 2u, which is going to give me a negative 2 minus 2u That is a great answer. We could, if we wanted to, factor it out of u and do a u plus 1 inside. It doesn't matter. But that's my Jacobian. That's what we're going to have to actually multiply by in our integral once we get to our integrals. That's what we'll multiply by in our integral to make our transformation accurate. All right, let's do one more. Notice that there are u's, v's, and w's now, and we have x, y, and z. This is, if you want, pause the video, and I want you to try to write the formula for the Jacobian. All right, so I'm going to write them in x with respect to u, x with respect to v, and x with respect to w, and then y with respect to u, y with respect to v, y with respect to w, and then we add our z's. Z with respect to u, z with respect to v, and then z with respect to w. This usually goes faster than it seems, depending on the functions. All right, so x with respect to u is 2. X with respect to v is 0. There's nothing there. And then with respect to w is 1. Then we do the middle term. Okay, I got 2u minus 2v, 0. The z's. All right, I got 1, 2v, and minus 4w. Okay, so I'm going to give you a way to find the determinant here. We have to put plus or minuses throughout here. All this does is going to go with the number that goes on the outside. These are the numbers that it's going to pick up. All I'm doing is alternating there, plus, minus, plus, minus, plus, minus. How I determine this now is this, I pick a row. I can pick any that I want. I'm going to pick this row, and let's do this column. All right, let's go run through the columns. So we'll do this, yeah. So what this means is the green tells me what sign to pick. So the Jacobian is a positive 2, and then times the determinant of the matrix on the inside. So 0, and you don't take up the green signs for this. It's only for the outside numbers. Okay, now I erase that, and I move over to my middle one, just like we did with cross products. Now this says minus, that's the green, and then whatever the number is, and then this doesn't even matter that these go in here. I don't use the green signs. I only use those for the number outside. Then I do my last one. Okay, that says plus 1, and then times that. 1, 2b, and then we just have a bunch of determinants. Okay, so 2 times 8vw minus 0, minus 0, plus 1 times 4uv plus 2v, and we get 16vw plus 4uv plus 2v. That is the Jacobian. This is what we would add to our integral, right? And we'd throw it in parentheses because we're going to multiply it all by it. But that's how you simply find a Jacobian. We're not going to get into the technicalities of why, because it involves linear algebra, which a lot of you guys have not had yet. So this is the Jacobian. This is the three-dimensional u sub. This would be the part of when we do u subs and we have to replace or we have to add a half or a fourth. This would be the equivalence of that. In most cases, these are going to be nice numbers once we get around to them. So